Hello, everybody, and welcome to another great day of PChem. So last time we talked about the shape and the formation of p orbitals. Today we're going to be taking a lot of these same ideas and just extending them a bit further with d orbitals. So as we've seen previously, we can separate out the radial components from the angular components of a wave function. So we're going to be mostly focusing in on the angular section of our d orbitals. And again, just a reminder, all of these can be derived from our spherical harmonics where we set the L equal to 2. However, one of the important features that we have to deal with here is that our M sub L can be one of one of 5 different values. It can either be 0, +1, or -1, +2, or -2. So this gives us 5 potential contributions, and we're going to be more or less examining each of these 3 sets independently. So let's go ahead and start with the simplest case, M sub L equals 0. So when I set my M sub L equals 0, this means I've got no angular momentum pointed in the z direction, which means I've got no dependence on phi. So my system essentially is going to show no movement in the xy xy plane. Instead, almost all of the movement is going to happen in the z plane, along the z-axis. So here we have just kind of this odd form, 3 cosine squared theta minus 1. So this is going to be a little bit of an odd form, and trying to spot the nodes and the peaks is a little bit tricky. So we can probably spot 2 peaks right away. That's going to be essentially when theta is equal to 0 or pi. This term goes, this cosine squared will go to 1. And then times 3 minus 1. Essentially, we get a value of 2 up or down. So we're going to get a really nice maximum there in the there at each end. We're also going to find a smaller maxima when theta equals pi halves. So normally that would send our function equal to 0. But that just sets the cosine portion equal to 0. So I'm going to actually have a negative wave function sitting there along the xy plane. So I'm going to have maximum density along the, when z is very hot, along my z-axis, both up with a positive, down with a negative, down also with a positive because of this squared function, and then a negative ring around the middle. I'm also going to have 2 nodes somewhere in the middle, essentially around about 0.2, 0.3 pi. Now, you probably know this orbital as the dz squared orbital. This is the quintessential joke of most general chemistry because this is the one you remember because this is the one that looks weird. Congratulations, this is the only d orbital that is an actual eigenfunction of angular momentum. So in fact, this is the truest of the d orbitals you typically know, where again, we have a positive wave function along the z-axis that kind of looks like a pz orbital, and then we've got a negative wave function sitting around the xy plane. So that pretty much gives us the z orbital. One of the things to note is even while I do have density in the xy plane, all of the movement is still going essentially up and down, because if it was going, if the movement actually occurred around in a ring, well, then I'd actually have an angular momentum, and that wouldn't give me an M sub L of 0. So important thing to note, we split the wave function in 2 bits, but all the movement is essentially going up and down in the z-axis, guaranteeing that all the angular momentum points out. So this brings us to our next set of orbitals, M sub L plus and minus 1. These ones actually are kind of fun because what we have here is, again, we now have a phi dependency. So the plus orbital means that I've got movement going around in the clockwise direction, again, as seen from below, where I've got movement in the opposite direction for the minus 1d orbital. But otherwise, they occupy the same physical space. Here, as you see, we can spot the nodes with a cosine theta, sine theta. So when cosine theta is equal to pi halves, we have essentially a node. So I've got a node of density cutting straight through the middle along the xy plane. So I won't find my electron there. But I also have a sine theta term, which means that if my angle gets too high, so I get too near the top of that z-axis, I also have no density. So essentially, this constrains my density to almost look like an x function with the legs of the x either pointed down or up, and then rotating. The direction of rotating dictates plus or minus wave function. However, as noted before, just like our p orbitals, neither of these functions actually exist in the real space. So it's difficult to draw this for your typical Gen Chem class. So what we do is we typically combine these two wave functions in a linear combination to generate orbitals that exist in the real space. So we can use them to generate our zy and our zx orbitals. So our yz orbital or zy orbital essentially is going to be adding these two wave functions together. Then what essentially happens is we're going to cancel out any probability density along the x-axis and reinforce any probability density along the y-plane. So one way you can think about this is my wave function exists as almost this in almost this X shape where it's wobbling back and forth. So it goes forward and backwards, forward and backwards. So I'm going to show net zero angular momentum in the z direction, but it does confine me into a discrete space. Again, rather like we saw for a particle in a box. Now, it is worth noting that in order to generate a relatively stationary probability density, I have to have equal amounts of motion going forward and backwards. And this is exactly what we see with our coefficients, with both set to 1 over square root of 2. I've got 1/2 of a contribution from the +1 and 1/2 from the -1. So essentially equal contributions of both these orbitals, directionality cancels out, and I have a stationary wave function. We have the similar effect with our xz orbitals. The biggest difference here is that when I add them together, when I combine the functions, we now use a negative contribution for my -1 wave function. And all this really does is change our offset to make sure that all of our wave function along the y-axis cancels out this time. And we confirm we guarantee that all the probability density happens here in that xz plane. Again, both of these functions, we've got no probability density pointing along either any of the z, y, or x axis. Instead, it bisects the two axes of interest. Now, that only gives us 3 wave functions so far. So we've got 2 more orbitals to consider. So we have our d-2 and d2. So in this case, all our probability density occurs in a ring around the nuclei. So I have a sine squared theta. So for sine squared theta, I'm only going to have a probability density. I'm going to have my largest probability density when theta equals pi halves. So again, along the xy plane. And very little probability density when theta goes to 0 or pi, so essentially near the z-axis, which helps push my system further out into this ring shape. Furthermore, here, my angular momentum in the z direction is going to be 2 h bar, but either plus if I'm moving this way, or minus if I'm moving the opposite way. So neither of these wave functions exist in real space, but I can combine them in a convincing way to generate my xy and x squared minus y squared orbitals. So the one with the odder name, x squared minus y squared, is conveniently and confusingly, I flipped them up here. So my x squared minus y squared essentially exists along the x and y axis. So that's kind of the reason for this odd notation. But confusingly is actually generated by adding the two wave functions together. Conversely, if I subtract my two wave functions, this gives me my xy orbital, which again, just like we saw with the dx z and dyz, essentially splits the relevant axes. So if I have dxy, it means I'm bisecting the x and y axes, because this is where this is essentially where I have the cancellation of wave functions. So by combining these two wave functions, I get a node along the axes, whereas here I get a node bisecting the systems. That said, you can imagine if I added these two wave functions together, I should be able to regenerate a uniform probability density all around my nuclei along the xy plane. And so this is more or less the key trick with trying to deal with with any high angular momentum orbitals. You can even apply this to f or g orbitals. However, then instead of just dealing with plus or minus 1 or plus or minus 2, you start introducing plus or minus 3 or plus or minus 4. And since we don't see that many f or g orbitals in chemistry, we're going to kind of leave off today with just looking at the d orbitals and their shapes. And again, one of the big take homes I want you to keep in mind is that when we look at those typical orbitals from Gen Chem, none of these are the actual eigenfunctions that are so useful in building up a probability density. Instead, they're a linear combination of our relevant wave functions. However, since the energy doesn't actually care about your value of m sub L or even L, it's actually fine to go ahead and combine these values and still have an eigenfunction of the Schrodinger equation, very similarly to how we treated the particle in a box, just a little bit more three-dimensional. So this brings us to the end of our orbital shapes and honestly our description of the hydrogenic system. Next time we have to deal with what do we do if I have an atom that has more than one electron? The answer gets a little bit messy. Until then, take care.